All right, in day 5, you're going to understand the definition of a polynomial and the connection between the degree and the degree of its rate of change. We're going to talk about x cubed, and we're going to talk about the degree of a polynomial, the sign of the leading coefficient to determine the end behavior. So here you have a table, and again we're going to take the rate of change. Here it's getting bigger by 1, bigger by 7, bigger by 19, bigger by 37, bigger by 61. Just subtract, and if it's growing it's positive, if it's getting smaller it's negative. These numbers don't look very interesting, but if we make the second differences, these are linear because there's a constant difference of 6. So since the first rate of change was linear, it's a quadratic. The second rate of change is linear, which is why we say it's a quadratic. And the third, we can say, is constant. So if something is third degree, the rate of change or difference is quadratic. If it's quartic, which is fourth degree, the rate of change is cubic. So it's always one less. Hopefully you remember from Algebra 2 that if we graph y equals x cubed, we can make a table and plot these points. Obviously 27 is off the graph, but we just put those numbers in so you can see the behavior of the function. And it goes left to right forever, and it goes up and down forever. Now in Algebra 2, we didn't make a table to graph everything. We graphed using what is called transformations. So in A, if you look at the green dots, that's the original graph. Then in blue here is the 2, so you double the y values. So the y value here is 2, negative 2, and then the y value here of 8 goes up to 16. This one goes down to negative 16. And we have our blue dots. And then the red, minus 3, takes the graph and moves it down 3. So 1, 2, 3. 1, 2, 3. 1, 2, 3. And we have our red graph, which is the result of the multiplying by 2 and subtracting 3. They want us below to find the x-intercept, y-intercept, domain and range. Well, left and right goes forever, up and down goes forever. That's true for all cubic functions. To find the x-intercept, I want to find the x and y is 0. So we plug in, add 3 to both sides, divide both sides by 2, and take the cube root. So there's the x-intercept. The y-intercept, we just plug in 0, but we can also see we went down 3, and it's 0, negative 3. For b, we have our green original function, our cubic function. The negative in front flips the graph over the x-axis. So this point goes down here, this point goes down here, the origin stays the same, this point down here goes up, and this point down here goes up, and we have the blue dots. In the red, we go to the right 3 and up 4. So we take each of those blue dots and go to the right 3 and up 4, and we get these points. Connect those and we have our graph. To find the x-intercept, y is 0, y is 0. If I kick this negative portion over, it becomes positive. Cube root both sides and get the x by itself, and I get the x-intercept. To find the y-intercept, I let x equal 0, and so this happens, and I get 31. So our y-intercept is 0, 31. For example 4, they want us to figure out what kind of function it is, find the inverse, and if it's even degree, we might need to restrict the domain. And we want to write the domain and range of the inverse, So as before, f of x becomes y, we switch x and y, and we solve for y. To get y by itself, I'll kick the 4 over, that's where the minus 4 comes from. I'll multiply both sides by 3/2 to get rid of the 2/3, and then I'll add 2 to get the y by itself, and y is the inverse of f. Since it's a line, it's going to go left and right forever and up and down forever. Third degree, it's cubic. Let the function become y, switch x and y. Cube root both sides to get rid of the 3. Subtract 7 and divide by 2. And y is by itself. In this case, since the function is g, we have the inverse function of g. And the original cubic function goes forever up and down and left up and down. So we switch the domain and range of the original function, we still get from negative infinity to infinity. Obviously, this is quadratic, it's second degree. Replace f of x with y, switch x and y, kick the 4 over. To get rid of the squared, I take the square root of both sides, and I get plus or minus. And then to get y by itself, I add 11. Well, since it's an even degree, I want this to be 1 to 1, so it'll be invertible, so I restrict the domain. So this parabola down here, if you remember, this is a parabola with its vertex set to the right 11 and up 4. So there's the vertex. When I flip it, it becomes sideways. It's a square root function. You might remember the square root function. And the x and the y switch. And so this is the inverse. It starts at 4 and goes to the right, the domain of the inverse. And the range of the inverse starts at 11 and goes up. Or, if you want to look at the original function, where the domain is 11 to infinity and the range is 4 to infinity, you just switch them. Whatever is easiest for you. Fourth degree might be new for you. That's quartic. Look at the word quart. And replace the function by y, switch x and y, kick the 3 over, divide by 5. To get rid of the 4th power, I take the 4th root of both sides. An even power produces a plus or minus, but to restrict the domain, I will only take the part to the right. A quartic is very similar to a quadratic. It's just steeper. There's other things that could happen. For this one, though, it's pretty simple. So it's going to have a vertex, you might say, of 0, 3. So the domain for this would be 0 to infinity, but that becomes the range for the inverse. And the range for this is 3 to infinity. That becomes the domain of the inverse.